Hello and welcome to part 3 of Dev Maths and Stats Refresher Course, Lecture 8. Here we're looking at some examples with particular numbers and specific distributions for expected value and variance and so on. So question 1 has got here a random variable x can take these particular values, so it's a discrete random variable, and for each of these values, these are the probabilities, those values. So 0.05% very unlikely of getting 3 and so on. So find the values of these things here, starting with just expected value of x. So if I was doing this, maybe I'd just calculate it on a spreadsheet. So I thought I'd show you that for a change, just so you have the calculations here, and then I can make the spreadsheet available to you. Here I've written x bar, which is a shorthand for is the expected value of x. That's the same thing. So when you see an x with a bar above it, that means the expected value of x. So to calculate this is the basic one. It's just each value of x times its probability. If you go back to linear algebra, it's the dot product of the x vector with the probability vector. So it's this times this, plus this times this, plus this times this. And it's built into Excel as this function, sum product, which automatically multiplies these values by these values and adds up as though it's a dot product. And here we can see it comes to 9.1. So it should sort of make intuitive sense to you. But this is the value which is the highest probability. These have lower probability, so the expected value is around about here somewhere. So that makes sense. Okay, now to find the expected value of 5x plus 5x minus 1, there's two ways we're going to do it. First of all, from the definition of this, and then using the formulas we've got for simplifying expected values. So let's do it the long way first. So to do this, to work out the expected value of any variable, what you need to do is to stuff like this. So I'm going to put in an extra column here, and this extra column is 5x minus 1. So it's just these values, 5 times this minus 1. So I've calculated those. I don't need another row of probabilities because the probabilities of these is the same as these, because the chance of x being this is the same as the chance of 5x minus 1 being this. So once I've done that, I can just multiply these to get the expected value of this column. So that's just that sum product, probabilities times the values. So it seems like the expected value there would be 44.5. The other way of getting that would be to remember what the equation we derived so laboriously, and say that, okay, that using the rules would be 5 times the expected value of x, minus 1. So you can split this into two pieces and extract the 5. So it should be like that. So you should be able to predict this result by saying, putting in a formula like this. So instead of calculating from fresh, just start from here and go 5 times this minus 1, and you get straight to the same thing. Okay. Right, the next question on here is expected value of x squared. Why we have to do that is, unfortunately, there's no short way of doing it because we haven't got a way of breaking that down. We have to actually calculate this the long way. The reason it's needed is because when you calculate variances, you're going to use it to get the variance here. So once you've got the variance, subtract this, and once you've got expected value of x squared, subtract mu squared, and then you have the variance. So you need to know how to calculate that. Let's go with the right spreadsheet, that's for later. So what you do, you make another column here. So it's x squared. So it's based on this number squared. You can see these are the squares. And then the expected value of this is just this times the probability, because the probabilities of all these are still given here. Once you've done that, so it's sum product of this times this, dot product, add those up and you get 88.2. So I think I've done this, I just did this one way. Here, to get the variance, you could do it the very long-winded way by calculating x minus the mu for every single every single possibility, but I think I just did it here the quick way. Yeah, so I've done this. So variance is equal to expected value of x squared minus this squared, which we already have. So that's using the slightly shorter way of getting to the variance. So that calculates the variance as 5.39. Okay, so that's that question. Question 1. Now let's hop over to question 2. And this one really doesn't really lend itself to Excel, so we'll do it on the whiteboard. Rather than going backwards and forwards, I think maybe we'll copy it across. Okay, so if we try to start up here. The probability density function is m over x squared. So to find the probability that z takes any particular value, you integrate between the two values. But we don't know what m is, so we need to find that first before we can do any working, as it says here. The clue is that z can only take values between 2 and 6. So the probability density function outside of that region is 0. So it means that all of the probability must be between 2 and 6. So if we do this, between 2 and 6, and integrate that, because it's not allowed to have any probability, it's not allowed to have a value outside of this. These are all the possibilities. So that probability must come to 1, because it's certain to lie between there and there. So we just have to do the integration, we can get m. So integrating this, we want to be it would be that if I'd written down the right thing. I was going to log. There's a squared there that I've forgotten. I was looking half familiar. So you want to be m squared goes when you integrate back to this, but that's not quite right, because if I differentiate this x to the power minus 1, I'll get to 2 x to the power minus 2, but I have to multiply by minus 1, so there's a minus 1 there. So that should be equal to 1. So I put these values in. So it'll be minus m over 6 minus m over 2. So in other words, because of this minus sign, it's better to work it out this way. Let's come back over to here. Right, let's keep it together. M over 2 minus m over 6 must be equal to 1. So you can put the whole thing over 6. So in other words, this is the same as 3m over 6. So 3m over 6 minus m over 6 is 2m over 6 equals 1. So m is equal to 3. So now we can have a look at part B. So the expected value of x over z, sorry, this is the random variable called z, is equal to the expected value of all the values of z, so between, and you need to go over every possible value, so it's between 2 and 6 again. And it's, you can use z, but we're using the variable x to the integration, so the value is x goes between 2 and 6, and you've got to multiply by the probability density function, which we now know is 3 over x squared dx, because 3 over x squared is the probability density function. So x times the probability, or x times probability density function of x dx between 2 and 6. So it simplifies a bit, because this cancels out, so it's 3 over x. Keep that cordoned off there. Here we go. So integrate this. And this way you are going to get log 3 log x, because log x differentiates onto 1 over x, and that's between 6 and 3. So it's going to be 3 log of 6 minus 3 log. Where is this 3 arrived from? This number's growing when I look at it. 2 minus 3 log of 2. And using your friendly laws of logs, if you take the 3 out as a common factor, that's 3 times log 6 minus log 2. So it's 3 times log 6 over 2. Log 6 minus log 2, 6 over 2. So it's 3 log 3, so it's log 3 cubed. It's log 27. So I suppose we ought to, that's a bit hard to work out, to imagine what sort of number log 27 is, so let's just zip off to Excel and just use this for a moment to get let's actually put it in proper format. So 3.296. So roughly 3.296, which sort of makes sense because it's between here and here. The probability is decreasing, so it's more likely to be towards the 2 end than it is towards the 6 end because the probability function is always decreasing. A bit like this blue line. Okay, let's go on to part C. So part C looks nasty, but in fact can be done extremely quickly. Expected value of 4z plus 10 is simply equal to 4 times the expected value of z plus 10. So it's going to be 4 log 27 plus 10. In other words, it's 4 times this plus 10. So if I left it on the spreadsheet, as I should have done, that's foolish. Let's see if it will come back to life. There we go. So it's this times 4 plus 10. 3.133. 3.133. Okay. And then finally part D, which is easy-ish. Part D, what var variance of z. So we use the rule that you can simplify this to get expected value of x squared minus mu squared, and mu is another word for this, so that's mu expected value. So you've got that already, this is already worked out. So it's just a question of working out the expected value of x squared, and that's quite nice because 26x squared, so x, the definition is it's wherever the thing you're trying to find the expected value is of times the probability density function, which is the same as the original one because the probability of getting this is just the same as probability of getting x. So times this by the probability density function dx. Oh no, well we know it's less of a mystery because you now know m is 3. This is looking very simple because it's just the integral between 2 and 6 of 3 because it all cancels out. So this is integrates to 3x. And that's going to be between 6 and 2 minus mu squared. Should be the minus mu squared here. got this part. Okay, we have to make some more room. So here you put these in, so it's 18 minus 6 minus mu squared log 27 squared, which is 16 minus this thing squared. So where is, I left it this time, equals 16 minus this thing to the power 2, 5.137. Is the variance of Z. Okay. Back to the questions. I think the rest of this is just done in Excel, so it's less fiddly. Yeah. So let's do this. I put the joint probability distribution shown into Excel and then calculated these things there. So I think the questions are also written on the spreadsheet, so we can just go and look at that thing over here again. Let's just zilch that for a moment. Gosh, I don't need that. I know that we finished that now. Yeah. So we're down here on this question. So there's here's the table. I've also added in the sum of these probabilities here. Okay, let's see. The first thing we're trying to find is the expected value of V given that U is 1. So in this situation, we're told that U is 1. So if U is 1, if U is 1, then what's the expected value of V? So in that case, we can't use these probabilities because these are the probabilities if we don't know what U is. So given that U is 1, we know we're on the top row. What are these three probabilities? What are the probabilities of these three values of V? We have to multiply V by the value the probability that V takes that. So it's 0 times the probability that V is 0 given that U is 1. And remember, you get that by doing this divided by this. Because we're using, I think I've written them down over here actually. Yeah. So I've done them already over here. So these are the values of V. Just to calculate it, I wrote the values of V down to make them vertical down here. And this is the probability of each one of these. So if I know that U is 1, probability of getting V as 0 is this divided by this, by Bayes' law, because that's what this is here is, it's the probability that, okay, let's actually get a pen rather than it's the probability that V is equal to 0 given that U is 1. That is the thing I want to multiply this by. So it's U times the probability of U being 0 given that I know U is 1, and this by Bayes' law is equal to the joint probability of V equals 0 or U equals 0, V equals 1. That's this one divided by the probability that U equals 1. That's the joint probability divided by this marginal probability, which is why it's this divided by this. And then similarly for the other ones, it's this divided by this and this divided by this. So you've got these three probabilities. and then just going to get the answer, you do the sum product of those. That gives you the expected value of v given that u is 1. Okay. Next thing we want to know is the covariance of u and v. And that we need a bit more information here. To get the covariance of u and v, we're going to use the formula from up here. The covariance is the expected value of xy, or uv in this case, minus the two expected values multiplied together. So we use that as a short way of getting at the covariance of u and v. So what you need here is the values of u and v. Is if you check these, this information is exactly the same as the information in this table. It's just written down in a column to make it easier to deal with. You'll get a lot of this later in a bigger spreadsheet. So that's the basic joint probability distribution. This is the thing I'm interested in, uv, so it's this multiplied by this, all the combinations, the 6 combinations there. The probability of these is the same as the probability of these. And then this is the u squares, this is the v squares, so I need those as well. So So I've done the different stages here. So first I need to know u bar, the expected value of u is u times its probabilities. Expected value of b is the values of v times the probability of that. So those are the two expected values. Expected value of u times v is just this column times that. And then from that I can get the covariance, which is just this minus this times this. This minus this times this, using that short method. So I think this is the first specific covariance we've looked at, and it's quite low. It's positive but quite low. This is just telling you the positive value that u tends to be higher when v is higher, and v tends to be higher when u is higher, and they tend to be lower when they're both lower. But it's a very, very low number. But how low is it? Let's judge that. Where's the covariance? Well, that's the next question. That's the covariance. Next question, as we can see just about off the bottom of the screen down here, is to convert this into correlation coefficient. So to convert it into correlation coefficient, you need to divide this by the standard deviations of u and v. So you can need to work out the variance and then square root those, which is why we've got these two columns up here. So first step, work out the expected value of u squared, which, surprise, surprise, is just probabilities times u squareds. And work out the same for v squared, so that's the expected value of v squared. And you can work out the variance of u by doing expected value of u squared minus its mean squared. Same for the next one down, variance. And then you pretty much look at all the ingredients. So the correlation coefficient is its covariance divided by the standard deviation of u and v. And to get the standard deviation, you take the square root of these two things. So that is your formula for changing covariance into correlation coefficient. Is just to divide the covariance by the square root of variance, another standard deviation of that, times the standard deviation of that on the bottom. And that standardizes it, so this will always be between -1 and +1. So you can see it's still pretty weak, but it's not as crazily weak as this seems to indicate. So maybe this is weak because of the small scale of the numbers, but this removes things like the size of the numbers and the units and so on. And it gives you the idea that it's weak, but it's not that incredibly weak. Still, there is some sort of positive correlation there, though it is very, very weak. Okay, so that I think is the end of those examples. So next we're going to go on to look at some demonstrations of these relationships between expected values and variance and covariance and so on, and to get some important identities that you'll find in econometric theory. But for now, thanks for watching.